In this video, we're going to introduce you to a number of simple concepts related to probability, and the focus is going to be on examples that you are already familiar with from everyday life, and then we'll gradually progress in the unit through to more complicated examples of probability. So I'd like to begin by looking at things that we know in life are impossible and have a 0% probability, all the way up to things that are certain, like 100% probability. And then we can look at some things along this spectrum too. We can express probability as a percentage, but it is commonly often, instead of a percentage, written as a decimal from 0 to 1. All right, so things that are impossible. Maybe you might say the probability of the poor Toronto Maple Leafs winning the Stanley Cup ever again is a 0% chance, ha ha ha. And then maybe for certain you might say, oh, within the next 10 years, it is most positive that the Montreal Canadiens will win the Stanley Cup, ha ha ha. With some fun examples. Let's look at some other ones that are maybe not so subjective in nature. Let's look at if you roll a die. You know that a die has 6 faces, and therefore the probability of getting any one of the values on a particular face is 1 in 6. You might look at the probability of flipping a coin as being a 50-50 chance or a 1 in 2 chance because of the two sides of that coin, and assuming the two sides are different, of course, and it's not a rigged coin. Maybe if you reach into a particular bag of Skittles or Smarties, you might have, if it's one of those little Halloween bags, maybe there's like a 4 in 5 chance that you're going to get a particular color. Maybe that color is red. Maybe that color is blue. Who knows? So 4 out of 5. We'll make the last one blue just for fun. Okay? 4 out of 5 chance. Okay? So again, we can express these as fractions. We can do them as a decimal between 0 and 1, or we can do them as percentages. Okay? In your notes, you also have beneath this introductory idea some big ideas of what empirical, theoretical, and subjective probability are, and I encourage you to read those as well, because we'll come back to them a number of times. Let's begin on page 2 then with some examples of probability. So let's begin first off with using some tree diagrams to help us see instances of probability. So it says here, find the probability of getting exactly 2 heads if your coin is tossed 3 times. So one of the things in probability is we need to identify what an event is. Okay? And in this case, the event, we'll call it event A, is going to be getting 2 heads in 3 tosses. And where we will let S be the total possible outcomes. So how many different ways could we actually end up with different faces of different coins if we do this? All right. So here's how a tree diagram could help us. If we begin with the first toss, I'll call it toss number 1 over here, we know that there are 2 possible outcomes from that toss. We're either going to get a head for that coin, or we're going to get a tail. Okay? If we move on to toss number 2, even if I got a head the first time, after the second toss, I've got a couple of options. I'm either going to get a head or a tail. And the same would be true if my first toss had a result of a tail as well. I could get a head or a tail. So far, there's only 1 out of these 4 possibilities that would be a double head. But because we have 3 tosses in order to have this happen, let's see what some other options might be. Well, again, if I follow this pathway, I could end up with a head or a tail in my third toss. Similarly, a head or tail here, and here, and here. So let's go through now and see how many of these pathways result in 2 heads. Okay, so this first pathway along here has 3 heads, so it does not meet the criteria. Okay, how about the next one? If I go heads, heads down here, yes. And if I follow every pathway, here I have head, tail, head, that would be a yes. Head, tail, tail will be a no. Tail, head, head would be a yes. Tail, head, tail would be a no. And the last two would also be no's. So, how many times does event A happen? Well, event A happens 3 times. What's the total number of tosses? Well, the total number of possibilities is 8. So we could say, therefore, the probability of getting 2 heads, and notice I'm going to use some short form notation to communicate this idea, would be 3 out of 8. No worries. Let's try another example. This one comes from the activity that begins this lesson on page 304 of your textbook. So I'm going to make the assumption that you've done the investigation, and doing it will help you understand the outcomes of this example as well. The game that you get to play in the investigation is you have one partner make 3 slips of paper, one that says a 1, a 2, a 3 on it, and so does another partner. They make their own set of 1, 2, 3s. Each partner has a little cup that they put their 1, 2s, and 3s into, and you play a game of each partner drawing out a number to see what happens, and partner A will get a point if the product of the 2 numbers is less than the sum. Player B will get it if the product is bigger than the sum, but if the product and the sum of those 2 numbers are equal, no one gets a point. So let's begin looking at the probability for each of these scenarios, either player A getting a point, player B getting a point, or neither of them getting a point. Let's begin by defining the 3 events. We're going to let event A be a point for player A. And just to refresh, that means that the sum of the 2 numbers that are drawn, one from each partner, is going to be greater than the product. Let's let event B be where a point is given for player B. So in other words, the product will be greater than the sum of those 2 numbers drawn. And then lastly, let's let event C be no points awarded. Sorry, the sun just came out. I'm just going to adjust the light a little bit so that it's a little easier for you to see. There we go. Okay. So we may find a tree diagram is very useful here as well. So let's look at what happens when the first number is drawn. Well, the first player is either going to draw out a 1 or a 2 or a 3 out of their cup. If the first player draws a 1, the second player will in turn either draw a 1, a 2, or a 3, and the same thing can happen all the way down here in our tree diagram as well. Okay, so you can see that there are 9 possible overall outcomes for this little game. Let's do a comparison between the product values and the sum values. I'm going to use P for product here, and I'll use S for sum here, and then we'll see who gets the point. Okay? So the product of these 2 is equal to 1, and their sum is equal to 2. Okay? And that would mean the sum is greater, which means that player A would end up getting the point in that particular set of events. Here, the product of them is 2 and 3. I'm going to do them both at the same time, save a little time. The sum is 1 plus 2 is 3, and 1 plus 3 is 4. So again, notice in all of these particular outcomes that player A gets a point. So in other words, when the first player draws a number 1, player A is always guaranteed a win. Let's look at the other scenarios. 2 times 1, 2 times 2, and 2 times 3 would be 2, 4, and 6 respectively. And then the sums would be 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5. So here again, the sum is greater than the product, so player A wins. Here they're both equal. That's event C. No one's going to get any points in that scenario. And then here, the product is larger than the sum. That means player B is going to get a point. And let's finish the last round here. So we have product being 3, 6, and 9, and the sum of those two numbers being 4, 5, and 6. So who gets a point? Looks like here, again, sum is greater than product. That's a point for player A. Here, product is bigger than sum. That's a point for player B. And similar scenario for the last one as well. All right, so let's take a look then at the probability for each of these scenarios happening. So the probability of event A, well, we noticed that there were 5 instances out of the total 9. So the number of events, or number of times player A got the point was 5. Out of the sum of all of the events together is 9. And we can leave it as a fraction, that's fine. You could do it as a decimal. It would be 0.5 repeater, but the fraction is okay too. Let's look at the probability for player B getting a point. Well, how many times does player B get that point out of the total number of times a point is awarded? Looks like B gets it 3 out of 9, or 0.3 repeater. Okay, so again, the probability can be written as a fraction, can be written in a decimal. We could also write it as a percentage as well if we round to the nearest whole percent for the purposes of this activity. Okay. Probability of no point being awarded. Well, the number of times that happens out of the total is 1 out of 9. So we have 0.1 repeater, or you could write it as a percentage, 11%. And so you should discover that all of the percentages add up to 100. All of the decimals, I know that they're repeating digits here. Okay, I'm not going to show the repeating digits, but they would all add up to 1. And all of the fractions would also add up to 1, so that all events are included. Okay, let's move on to example 3. In example 3, I want to go to the game of Monopoly. And the reason I'm going to the game of Monopoly is because it's a game that often uses 2 dice. If you've played Monopoly, you're familiar with the idea of rolling 7, 11, or doubles to get out of jail. So what is the probability of rolling 7, 11, or doubles if you want to get out of jail in Monopoly? Well, what I find for this is drawing a diagram of, or a grid of all the scenarios of when you have your first die outcome and your second die outcome is very useful. And we're going to come back to this grid many, many times throughout the unit, so it's a good time to introduce it. Okay? So for the first die, you could roll a 1, a 2, a 3, a 4, a 5, or a 6. And the same thing with the second die. You could do a 1, a 2, a 3, a 4, a 5, or a 6. And when you're rolling the 2 die, you often add them together. So 1 plus 1 is 2. And we can work our way all the way across. If you want to pause the video to fill this in, you certainly can. I'm going to go through it quickly to fill it in so we can begin further discussion about it. There we go. So let's define what the events are. Okay, first event is we need to let A be the event of 7, 11, or doubles. And we're going to let S be the total number of outcomes. So already you might be able to see that the total number of outcomes is a 6 by 6 grid, which is 36. I'm going to add that in right here. All right, let's go through our grid and find out where the scenarios are that are sevens, or sums that are 7 first of all. So I notice that the sevens will end up being along a diagonal right here. Okay, so the sevens, there are 6 out of 36 possible times that could happen. For the 11s, I notice that there are only 2. They're right here. 2 out of 36. And for doubles, I notice that they actually happen along a diagonal this way. 1 plus 1, 2 plus 2, 3 plus 3, all the way up to 6 plus 6. And so doubles also has an outcome of 6 out of 36. Okay, so what's our probability then of getting a sum of 7, a sum of 11, or a sum of that involves doubles? Well, the number of outcomes where we got a 7 was 6. The number of outcomes where we got 11 was 2. The number of outcomes where we got doubles was 6. And as we said, the total number of outcomes for this scenario is 36. Okay, so the probability of getting a 7, 11, or doubles is equal to the sum of all of those, which is 6 plus 2 plus 6 out of our total of 36. That means that there are 14 ways to have something colored here in the grid out of 36. If we reduce that down to lowest terms, they both are divisible by 2, so we get 7 out of 18 if we write it as a fraction. If we use our calculators, we can get that as 0.38 repeater as a decimal, or if you want it as a percent, it comes out to 38.8 repeater percent. So again, you can communicate your probability using any one of those 3 ways of showing it. All right, last example. Sometimes we're interested not just in the probability of something happening, but also the probability of something not happening. And the name for that is called the complement. And so the complement is easy to find sometimes. If you know the opportunities that will happen, you can subtract them from 1 or from 100, depending if you're working with a decimal, fraction, or a percentage. Okay, so the complement, sorry, I'm just fighting with the sun here. Here we go. The complement, or the idea of something not happening, can be calculated. This is the event A not happening from 1 minus the probability of event A happening. All right, so let's say that you have the numbers 1 to 20, inclusive of 1 and 20, and we want to know what is the probability of not getting a prime number. So maybe you want to find out, well, what is the probability of getting a prime number? Okay, so maybe what we should do is let's list what are those prime numbers that you can find between 1 and 20 inclusive. Now 1 is a funny one. 1 is divisible by 1 and it is divisible by itself, which is 1. But because that number 1 is the same under both of those conditions, it's actually not considered to be a prime number. So we're going to begin with the next number would be 2. 2 is only divisible by 1 and itself. Next would be 3. Can you think of what would come next? Working up to 20. 4 would not be a prime number. 5 is. 6 is not. It's even. 7 would be next. 8 is even, so it's not a prime number. 9 is divisible by 3. 10 is even. We get 11. 12 is definitely not prime. It's got a couple of different factors. We'd have 13 next. 14 is even. 15 is divisible by 5 and 3. 16 has lots of factors. 17 would be next. And I'm going to jump up to 19. Okay, so there's our list. So if we want to know the probability of not getting a prime number, maybe we could write it like this, not prime. Well, there are 20 opportunities altogether here, there are 20 altogether, and 1 minus the probability of getting a prime number would give us the ones, therefore, that are not prime numbers. So we have 1 minus, and we have 8 listed here out of 20 numbers if we do 1 to 20 inclusive. Okay. Note that between 1 and 20 could also mean not inclusive, and we could do it the same way. Okay, I would be very clear as to whether I want you to be inclusive or between two numbers, which would actually then be 2 to 19. Okay, so when we're subtracting fractions, these right now are different sizes. This is wholes, this is 20ths. I can only add or subtract if the sizes of those pieces are the same. So there are 20 20ths in one, 8 20ths that are prime. That means that there must be 12 out of those 20 numbers that are not prime. Okay, we can reduce that down to being 6 out of 10 if we divide by 2. That's not the greatest common factor. We can divide these each by 2 again, or in other words, we could have divided by 4, and therefore it comes out to 3 out of 5. Okay, which you could also write as 0.6. 0 is a decimal, or you could write as 60% if you want to write it as a fraction. So the probability of not getting a prime number is 60%. The probability of getting a prime number is 8 out of 20. And there you have it, some common examples to get you started on probability problems. Enjoy!